So before beginning this lecture, just a quick recap of what we have done so far. So after learning the number systems and all those things, so we came to understanding the logic gates. So the Boolean algebra. The Boolean algebra was the algebra of the logic variables, and then we saw some logic gates, which are basically some logical operations as well as some special functions on the logic variables, giving rise to some logical output. So after we understood such gates, we also had an understanding of how we represent the gates symbolically, and how we can actually physically implement the gates using transistors. So now we are in a position where given any logical function, we would be able to implement that function using a logic gate circuit, and that means using electronic logic gates as well. So uh, so that is where we have come now, and in between we also have learnt about minimization of logical expressions. So whatever logical function we have in our hand for implementation, we can basically do a reduction or a minimization of that function so that we can use a most economical circuit. So that is one part. So now we would be diving into actual example circuits, which we will look into the design of those circuits and how the circuits actually behave in order to give out the required objective of that particular circuit. So let us start this lecture, and the first one idea one needs to develop. So we are dealing with what is called the combinational circuit design. So there are two parts basically, one is the combinational circuit design and another is the sequential circuit design. So first we will deal with the combinational circuit design. So what is here actually? So we have either a SOP or a POS expression, and we simplify that using your Boolean theorems, or a K-map, or from a truth table. So from anywhere, from somewhere, we would be able to get a logic expression. So that logic expression can be designed in a digital logic circuit. So we know how to do this. If we have a logic expression, we can draw the digital logic circuit. And we also know that sometimes we can be asked to use only NAND gates or only NOR gates or only and OR gates. So if we have certain constrictions or certain constraints, then we have to manipulate this logical expression in such a way that we are only working with those logic gates which we are given with. So that is also we know we can do that sort of manipulation. Now this sort of a thing, uh, where we have simply a circuit using logic gates, where we are noting down the input and output relationship without any memory of past outputs, that means the present output will not depend on what the actual state, what the past state of the system was, what the past outputs of the logic gates were. It will not depend on that. It will simply depend on what excitation, what inputs you have given just now. So that input will get converted to some output through the digital logic circuit, and it will not depend on any prior prior states of the logic gate outputs. Okay. So if that is the case, then we say that we have a combinational circuit design. So it simply depends on the present input signals, not anything else. So keep that in mind. When we come to sequential circuit design, actually you will understand the difference in a better way when we look into what the sequential circuit design problem is. So going ahead, we first explore the design, the logic circuit design of a half adder. So what is a half adder? So here in half adder, so half adder is an addition with no carry input. Now when we add, so you are adding 2 bits, so you can add a 1 with a 1, a 0 with a 0, a 0 with a 1, or a 1 with a 0. So you have only 2 bits, one is a bit and another is a B bit. So you can add, so A can be 0, B can be 0, A can be 1, B can be 1, like this, all these possibilities are there. So this we know would give me a 0, this we know would give me a 0 with a carry of 1. So I write it like this. This would give me a 1, this would give me a 1 with a carry of 0, with a carry of 0, with a carry of 0 here also. So there are two things, one is the carry bit, another is the sum bit or the result bit, carry bit and the sum bit. So you see here, note down here, we have simply written this. So 0 and 0, if we add these 2 bits, what we are getting as the sum and the carry, and similarly for all other combinations we have written down the sum and the carry. So this is what a simple addition was. This is simply 2 bits we have taken and added them. However, when we form a table, now we can say that this is a table which will give me a logic expression if I consider these zeros to be logically low and ones to be logically high. So this is basically giving me a logic expression also. So there would be a circuit, if I implement this circuit. So if a circuit be implemented using this particular truth table, then if you supply inputs to that circuit, the outputs will give you the sum and the carry of the addition of these 2 bits, of these 2 inputs. So the inputs are the bits, right? So this circuit will give you, so A and B you supply to this circuit, and this circuit will give you out the sum and the carry bit. So let us see what that circuit would be. So to do that, we simply note down the min term expressions, that's all. So S, what are the min terms? The min terms are A dashed B and A B dashed. Min terms, those whose outputs are 1, only those we are taking. So A dashed B and A B dashed. Similarly, so this is basically a XOR gate, and for the carry we have simply, you see, A into B. So it is basically a AND gate. So this is the circuit for the half adder, very simple. So how, if you are asked to find out the half adder circuit, so you have to first write down the truth table, from there you have to find an expression, and from there you have to write down the or draw the circuit. For any system, for any problem you have to understand how you can form the truth table. So half adder, you have to first understand the problem, what is half addition. So once you know half addition, so it is an addition of simply 2 bits without any input carry. Basically here no input carry is there. When I talk about the full adder, you will see the difference. But the fundamental thing is that given a problem, so from that problem you have to figure out the truth table. From that problem you have to figure out the truth table, and once you get the truth table, you will get a logic expression, and from there you will get a logic circuit. So that is the way to go. Always you will first start with understanding the problem. From the problem you have to write down the truth table, from there logic expression, from there logic circuit. So there can be a lot of other mathematical arithmetic problems like multiplication of 2 bits or subtraction of 2 bits. So this sort of problems can also be given. Okay, so you should be ready to to take those problems and solve those problems, find out the logic circuits for those problems. So this is half adder. Now we come to another alternative representation of half adder, where we are using only AND or NOT gates. So the XOR gate is not available to us. We have to only use AND or NOT gates. So only using AND or NOT gates is basically actually we are using the canonical form here. The canonical form we are using. So you see we are using the sum terms and then multiplying these sum terms together. Similarly here we have simply a product term. So sum and product. So AND and OR means only using AND and OR means you have to do either a sum and the product. So either you have to OR and do some AND operation. So that's all. So this thing we can implement in this manner also, as well as we can make it in this manner and then implement. So whatever way we want to do. So this is the implementation circuit. So next this is a problem where we want to use only NAND gates. So when we want to use only NAND gates, then the expressions have to be formulated in terms of NAND gates. So here you see this expression can be formed in this manner where every particular block is a NAND gate block. So this is the NAND gate, this is the NAND gate, then this is also an AND, this is also an AND, and this is also an AND. So all are NANDs. Here this is an AND, then this is also an AND, and we get that the basic thing is the A dot N and B. N and B we have to do, and then again we have to find A and with the output of the A NAND B we are again doing a NAND operation. Here again we are NAND operation, and then again a NAND operation, we are getting the output S. And from this and this, if you do another NAND A and B, from A and B if you do another NAND operation, we are getting this is N and B, and that we go through another NAND and we get the output. So in this way, for any problem one can ask you to implement with only NAND gates or only NOR gates or only AND or OR gates, so like that. So whatever way one asks you to implement, you have to reframe the logical expression in that term. So that manipulation skill you need to develop. This is a skill one needs to develop. By looking at a few examples and doing some practice, one can develop this skill. Now comes the full adder. So in the half adder we were only adding 2 bits. In the full adder there is always a C-in, a carry in. So normally if you have a word and you add, you are taking 2 bits at a time, right? You are taking 2 bits at a time, but during the addition you will generate a carry bit. Like here you will generate a carry bit. So normally when I am adding 2 numbers, I am actually adding 3 bits. I have to have an option of adding 3 bits when I am adding 2 binary numbers. So I have to have an option of adding 3 bits. So that is the option given here in full adder. And the initial carry bit is always 0. So this is the case, and for each addition, I will have a 0 0 0 0 here, and another set where I will have a 1 1 1 1 here, and the same things, the same addition. So if I am able to understand what is the outputs of all these additions, then I will be able to form a truth table, and this is what exactly has been done in this particular truth table. You check out the addition now. Each 3 bit is added to get a sum bit and a carry out bit. Carry out, this is the carry out. So each set of 3 bits is added to get a sum and the carry out bit. So Now looking at this expression, looking at the sum and looking at the outputs, which are the sum and the carry out, we can formulate the logic expressions. So we have simply collected the min terms. We have not tried to do any K-map or any other reduction. We have simply collected the min terms here, if you notice. And once we have collected the min terms, now we are trying to combine them by doing some manipulations in the expression. So we have done some combinations. So we have done the combination in such a way that ultimately we have got this expression. You check this combination. This is very easy to check. I will not spend my time here. So you can check this combination. Ultimately your S is becoming Ci, which is the carry in, XORed with A XOR B. So you have to do a XOR B first, then XOR it with a carry in, with the carry in. And C out, after collecting the min terms and doing some manipulation, you will see that C out is actually C in and A XOR B or A and B. Okay. Now you simply try to remember the half adder circuit, the first circuit that I showed. What was the sum there for the half adder? Okay, it was A XOR B. What was the carry there? It was A and B, right? You see, this is the output of the half adder. So if you pass A and B through the half adder, you will get these outputs anyway. So why not use two half adders in order to form a full adder? So we don't have to form a separate circuit anymore. We can use a lower order circuit to form a higher order circuit. So this is a very popular and very useful idea that is widely used in digital electronic circuit implementation. A lower order circuit is used to form a higher order circuit. Here half adders will be used to form a full adder. Now you see, the XOR operation is already present in the half adder. So after doing the XOR in the first half adder, if you take the output of this and take the C in and pass it to the second half adder, then there would be another XOR operation happening and you will get the final sum from the output of the second half adder. Similarly here you will get an AND operation from the second half adder and the AND operation from the first half adder. You need to add an additional OR gate. This was not in the half adders. So that additional OR gate has to be added and you will get your circuit. Let us look at the circuit by noting down the expressions. So you see, this is what exactly has been done. So this is A XOR B. This is A and B. Remember the half adder expressions, okay, sum and the carry. So now if you pass your next in your next half adder, one input is A XOR B, another input is C in. So what you get here, you will get C in XOR of A XOR B. Sorry, this is here, this one. You get this here, and what you get here, you would get C in dot A XOR B on this line, and this expression is this one or of this one. So you put a OR gate here and you get the C out. This is already got obtained. So this is how you can obtain full adder with half adders. You may have used some other circuit, so you can actually develop a different circuit starting from here. You do your reduction, you can simply implement the min terms, that is also fine. You do a K-map reduction, you will get some expression, that is also fine. Okay, everything is fine. However, why we have manipulated the expression in this way? Because the half adder circuit already we have developed. So why not use it to make a full adder? So always the engineer's mind will look in this direction, whether I have a simpler circuit and I can utilize that entire circuit block and form a larger circuit which has additional functionalities. This is exactly what is done, and this is, you will see in the combination circuit design, all the examples that we'll do will have this idea implemented there again and again. So this is a very important idea. So yeah, so here comes the end of this lecture, and here I have only restricted myself to full adder and half adders because this is the basic building block of arithmetic circuits, full adder and half adders. Okay, so one needs to understand the basic thing is here that this is addition of 2 bits only, not a entire full length word. Here there are only 2 bits getting added in this circuit. A and B are only 2 bits, only single bits. A is a single bit, B is a single bit which can take value 0 or 1, 0 or 1. Single bit addition is happening. There can be half addition where we don't have a carry bit. There can be full addition where we have a carry bit. So with this difference, with this important thing stated, we would move ahead to the next lecture where we will add full length numbers, and that is different. So please remember this. So full adder and half adders are for single bit additions, and there are other adders which we will use for full length word additions. Okay, that will take up in the next lecture. So thank you for your attention.